I don't know why, but this thing keeps on just shoving slides over. But anyway, so the next big law that we have in fluid mechanics is known as Stokes's law. So if you've done Calc 3, you might have heard of Stokes's theorem. Stokes's theorem is named after the same fella, as far as I remember, but Stokes's law is completely different. So imagine we have a spherical point mass with a low Reynolds number. So something that it tends to be stationary, but it can move slightly as well. Stokes's law states that the point mass, uh, or the drag of the drag of the point mass is proportional to the viscosity, radius of sphere, and the flow velocity of the fluid relative to the object. So that's where relative velocity comes in. It is a part of physics technically, but I just kind of left it out. But it's essentially how fast the object is going within a medium. So, for instance, if something is going 5 meters per second to the right, but there's something repelling it with a speed of 3 meters to the left, it will have 5 minus 3 or 2 meters per second to the right of net velocity. So, we should note that d is proportional to the coefficient of viscosity, the radius of the sphere, and the velocity. The proportionality constant is 6 pi. So it is quite a clunky equation, but it is fairly okay to manipulate and solve. We can also use this law in particular, we can use a thing called a viscometer to actually measure the viscosity of a fluid, utilizing Stokes' law. We can find the drag force on it by using the force as mass by acceleration, and then use the radius of the sphere velocity and then the 6 pi to find the particular uh, velocity of the object, or not velocity, the viscosity, not velocity, the viscosity of the object you can find. Hopefully, it should be clear that you can represent the viscosity as drag divided by 6 pi r relative velocity.